types of chemical reactions. And there's 5 primary types of chemical reactions: synthesis, combustion, decomposition, single replacement, and double replacement. Now, please note that they used to hyphenate single and double replacement reactions. That is no longer the standard, so please don't hyphenate. So as I said, there's 5 types of chemical reactions. There's synthesis, combustion, decomposition, and then I'm going to put a little line here, because when we talk about single and double replacement reactions, the color coding gets a little different. And then we have single replacement, and double replacement. And this is where I'm going to start color coding, because color coding, each different type of reaction has a formula that kind of goes with it. And I say formula in a very loose sense, because the formula will tell you what to look for when looking at either a written equation or a word equation onto how to tell what reaction's what. And if you're given part of a formula, you should be able to complete the other part of the formula. So I'll show you what that means. But first, we have to kind of write our key, and our keys kind of change because we're looking at different things. So for the 5 types of chemical reactions, the first 3 we're going to talk about are synthesis, combustion, decomposition. And for these formulas, A is going to be an element or compound, and B is going to be an element or compound. So we'll be talking about these, but for these, when we're writing them, please note that for synthesis, combustion, decomposition, A is an element and compound, and B is an element or compound. When we talk about single and double replacement, A is going to be a cation or ammonium. And B is also going to be a cation or ammonium. Then, put these right here. Then we have to look at, there's 2 additional parts of single and double replacement. You have your X, and your X is your anion or polyatomic. And then you have a Y. And that is going to be, that's the same color, oops, sorry. Is going to also be an anion or polyatomic. Okay. Another important aspect that we're going to talk about and we're going to look at, I'm going to kind of put a little box down here, is H2O. So H2O can split into OH and H2. That would be gas. And then you can go the other way. So OH and H2 gas might make H2O. And we'll look at this, but this is an important caveat to especially these types of reactions on sometimes how things might look different, but you really are being split because of how it's being written. And we'll look at that. But this is our outline for our notes. Okay, so as we dive deeper into chemical reactions, the first one we're going to talk about is synthesis. And the synthesis reaction is a chemical reaction in which two or more products react to form a single product. So they do A plus B forms AB. And please note that synthesis can occur between elements and or compounds. So you can add element and element, compound and compound, element and compound. You always end up with a compound. So your reactants are always elements, a mixture of elements and compounds, and it could be one or more. So it's many things becoming one. So let us go ahead and write down our synthesis reaction on our sheet here, where it becomes A. So it's A, and this is where you're color coding, plus B. So many things, A plus B, you're adding things together, forms AB. And please note on your key over here, A is either an element or compound, or B is an element or compound. So if you're following element plus element will form compound, element plus compound will form a bigger compound, and then you can have a compound plus a compound. But it doesn't always have to be two over here. It's basically multiple things turning into one thing is a synthesis reaction. So as we look more into synthesis reactions, we can look at some examples. Yes, these are all balanced, and we will be talking about how to balance soon. But remember, when you're looking at reactions, this could be either in written or word form. It's when you have multiple things like magnesium and oxygen gas form magnesium oxide. Hydrogen gas plus oxygen gas forms dihydrogen monoxide. Potassium and chlorine form potassium chloride. Iron and oxygen gas form iron 3 oxide. Calcium oxide and carbon dioxide form calcium carbonate. Sodium oxide and carbon dioxide form sodium carbonate. Potassium chloride and oxygen gas forms potassium chloride. You're looking at these as multiple things on one side and then just one thing on the other. Okay, so now this is a cool table. We'll be adding one for each type of reaction, and at the end, you'll have an entire table of reactions. So we can wait till the end to take a screenshot or type it down, but it's going to give the class of reaction, your reactants, and your products. So let's talk about a combustion reaction, because combustion reactions are interesting reactions. They don't really have a strong formula. They have things to look for. So for a combustion reaction, you're going to always be combined with oxygen. You're going to have a heat or energy source, and then you're might be releasing heat or energy. Think of combustion as like your combustion engine for gas. It leaks water and it has smog coming out. Most of them are synthesis, but not all. So let's take a deeper look into combustion reactions. So for a combustion reaction, we're really not going to be using these A's or B's because we're going to be writing down what we're going to be looking for. So a combustion reaction almost always will have a hydrocarbon, and a hydrocarbon is exactly what it sounds like, a hydrogen mixed with a carbon. So you're going to have some form of hydrogen and carbon mix. So that CXHY denotes that carbons being mixed with hydrogen. It's the formula for hydrocarbons, or the shorthand of here comes a hydrocarbon. You're going to be adding a hydrocarbon to, for sure, oxygen. We know that there has to be oxygen gas in a combustion reaction. We know that. That does not ever change. There has to be oxygen gas. So we often mix a hydrocarbon with an oxygen gas, and then we get our products. So we get our products. Your products might be another hydrocarbon or a byproduct, but it's not always there. So I'm going to put a question mark there because there might be a third byproduct or there may not, but there will for sure be carbon dioxide. So if you're looking for CO2 gas, that'll for sure be a byproduct of your combustion reaction. And there will for sure be water. That will also for sure be a reactant of your combustion reaction. And often you're going to get heat there because combustion kind of relies on heat to make it work. Okay, so let's look at some examples of the combustion reaction. As we discussed, there's going to be some form of hydrocarbon. So if you kind of look, the CXHY, as I said before, denotes hydrocarbon. But here's an actual hydrocarbon, CH4, C2H6, C2H12O6. So they added an oxygen. That doesn't necessarily mean if they add something to the hydrocarbon, there's going to be something additional, but sometimes there is. So if you look at this N2O4, you end up with NO2. And if you look at, there's like the sulfur here that has to go somewhere. It's not going to go into carbon dioxide or water. So you're going to get that extra byproduct I was talking about. But that's kind of what you can look for that extra byproduct as something being added to your hydrocarbon. If you're looking at carbon dioxide and water, notice there's always going to be carbon dioxide and water on the reactant side. And sometimes you have that extra byproduct if there's that extra product over here on the product side, the reactant side. And then you always have the oxygen gas. Okay, so now let's talk about our table again. So remember, synthesis has two or more substances, so that makes one compound. Your combustion, you're mixing things together with oxygen. They get carbon dioxide, water, and then potential oxide of something else. But now we can talk about decomposition reaction. This is when a single compound breaks down into two or more elements or compounds. So it's the exact opposite of synthesis. Synthesis, multiple things make one compound. In decomposition, one thing makes multiple compounds. And please note, for decomposition reactions, you really do often need an energy source because things don't like to break apart just by themselves. So you need heat, light, electricity. If you compost, if you go feel the compost bin, it's really hot because it's releasing energy, and that heat is, helping with the composting. Let's look at what a formula for a decomposition reaction might look like. So we're looking at a decomposition reaction formula. We're going back to our A and B formula. So it's going to be A, B, because it's going to be a compound, and that's why they're all put together. And it's going to decompose, and there's going to be some form of heat potentially here. Heat, light, electricity, and that's going to be A plus B. So as a breakdown, synthesis, multiple things become one. So A plus B forms AB. Combustion, hydrocarbon plus oxygen gas forms carbon dioxide and water. You might have something else here if there's something added to your hydrocarbon. Your decomposition reaction is A plus B forms AB forms A plus B, one thing becoming multiple things. So here are some good examples of a decomposition reaction. Notice on your reactant side, you have just one item. You have, mercury 2 oxide, water, magnesium chloride, iron 2 sulfide, calcium carbonate, sodium carbonate, potassium chloride, barium chlorate, and then those one things become two or more things over here on the product side. So if we're looking again at our reaction table, decomposition starts with one compound and ends up with two or more elements or compounds. Because remember, your A and B can either be an element or a compound. But now we're going to talk about single replacement reactions. And remember, we're not using the hyphen. And although it can also be called a replacement reaction, let's keep calling it a single replacement reaction so that you understand whether you're doing a single replacement or a double replacement. And this is legitimately a reaction where one atom completely replaces the atoms of another. Basically, it's switching another way of thinking of it, it's switching switching anions. Your anion is going from one cation to another cation. So if we're going to look at it on our chart that we're making, now remember down here I did this line, and now our A's are cations or ammoniums, our B are cations or ammoniums. And remember, when we talk about metals, metals are cations. Every cation is a metal. You have X as your anion or your polyatomic, and Y as your anion or your polyatomic. So remember, this chart goes for these down here. And so when we're looking at this, we have the idea is A and then X. So you start with an ionic compound, AX, and you're adding another cation or ammonium to it, and you're adding that because metals can stand alone. So it's okay that a metal's standing alone. So you're going to have AX plus B, and what's going to happen is this X is going to go over to the B. So this A at the end will end up standing alone, so it'll be A. So the A that was in a compound is now by itself, and that B now will be in a compound, an ionic compound with X. So they just the anion just switches places. So I'm going to point you down here because we talked about it earlier, but sometimes when the switch is happening, and we'll look at specific examples in a minute, like it might be H2O plus something. Well, remember, hydrogen is funky. It kind of acts as both an anion and a cation. So when it switches, the OH and the H2 get pulled apart. Or sometimes when they get added together, it becomes H2O. So we're going to look for that. That's why sometimes it isn't as clear as the switch is happening, because you have to look for the water. So let's look at some examples of single replacement reactions. So if you're looking here, copper plus silver 1 nitrate becomes silver plus copper 2 nitrate. The silver and the copper switch places because the nitrate switched from the silver to the copper. Here's iron and copper. Look here, the nitrate moves from the copper to the iron. Remember, I was talking about when you're switching with water, it can look funny. So here's calcium that was added to water. Well, it does do a replacement switch. It pulls out the hydroxide, because remember, water is two H's and 1 O, and OH is hydroxide, and that is your anion. So it pulls out the hydroxide and leaves hydrogen gas. If you think back to when we put calcium in water, and there was that white chalky stuff, and there was bubbles, and how we could light it on fire, those bubbles were hydrogen gas, and that white chalky stuff with calcium hydroxide. So you actually saw this reaction in person. Here's zinc and hydrochloric acid becomes zinc chloride and hydrogen gas. Often when you see hydrogen, it'll often turn to hydrogen gas. Zinc sulfide and oxygen becomes zinc oxide and sulfur. Look, here's another one with water. So to add potassium to water becomes potassium hydroxide and hydrogen gas. We also saw this one, but it kind of exploded on us. We have iron and hydrochloric acid becomes iron 3 chloride and hydrogen gas. And then sodium iodide and bromine becomes sodium bromide and iodine gas. So again, we're going to be adding to this table till we get to a table of 5. A single replacement is a metal in a compound and non-metal in a compound. And I know it says a non-metal, but that's more like when you're talking about things mixed with hydrogen, which is still a cation and is still an ionic compound, but hydrogen isn't necessarily either a metal or a non-metal. Hydrogen's hydrogen. And then you get your switched compound. So let's talk about double replacement reactions because these are very interesting beasties. So you're adding, it's two ionic compounds which switch your anions. So A and B are cations, Y and X are anions. Now, when we're talking about ionic reactions, I know all products of double replacement reactions are either a precipitate gas or water, but that does not mean that AX and BY are both going to be precipitate gas or water. Those are the only products available if it makes a product. So let's look at what this will look like in your reaction. So our double replacement here, we have AX. Remember, we're keeping the same colors that we did before, AX. And then you're adding that to BY. So both AX and BY, these are both ionic compounds. So if you see two ionic compounds mixed together, you're gonna have a double replacement. Then you're gonna have AY and that's going to be added to BX. Because the anions switch places. Now, over on the reactant side, these are more than likely going to be aqueous. Because when they're added to aqueous solutions, that allows the ions to break apart and reassemble. So both of these solutions will probably be aqueous. If we're looking at the product side, it's going to be a solid for one or both, a liquid for one or both, or a gas for one or both. If it is not one of these, it's going to remain aqueous, and both may be aqueous if no reaction actually takes place. Okay, so let's talk about when you're faced with a double replacement reaction, or you're given part of a double replacement reaction, like you're given AX plus BY, how do you know what AY plus BX is going to be? So the first thing you have to do is identify the components of the reactants. So basically, you have to figure out what the cations are and what the anions are. So this is where color coding becomes really important and really helps. You can either highlight or underline, but I'm going to recommend that you color code them and keep using your 4 different colors so that you can follow them when you're switching them. Then you're going to pair up your cations and anions with the other compound. So you're going to take your A and mix it with Y, and your B and mix it with X. And then you're going to write the formulas for the products using your pairs from step 3. And then you're just going to write the complete equation and then balance it once you've learned how to balance reactions. Okay, so let's look at some examples. So notice that if you switch like a hydroxide and a sulfate, but there's a water, H2 here, it's going to form water, and that's a liquid. So those hydrogen and hydroxide ones we've talked about maintain. If you look down here, sometimes it creates 3, and that is okay. You will not be expected to know which ones form 3. I'll tell you if they do form 3, and they form 3 simply because there's a water possibility, and usually where there's a water possibility, it becomes a possibility. So these are your examples for double replacement. Notice the anion switch, so hydroxide and sulfate, chlorine and sulfur, chloride and sulfate, chlorine and nitrate, carbonate and chloride, sulfite and nitrate, chlorine and hydroxide. And if you look at this, here's your final big chart of all the different reactions. We've added synthesis, which is 2 or more become 1, combustion, we have broken down, decomposition, 1 becomes 2, single replacement, a metal in a compound mixes with a non-metal in a potential compound, and there's a replacement that occurs, and double replacement, 2 compounds, which are 2 different compounds.